So whenever you have a multi-valued function, such as log z, you'll always find that somewhere in the complex plane that function will have a line where you have a discontinuity. So if you think about it, if we got our complex plane, well, this is real z, imaginary z, then if you take a point which starts here, say at r equals 1, theta equals 0, and you consider what happens as you move that point around, and you think what happens to log z as you follow this path. Okay, so we'll say r is 1, so we can just think, well, log z is just equal to I times theta. Now, theta is this angle here, which is gradually increasing from 0 up to, and then it reaches pi. So log z at this point is approaching I pi. But then, if we're taking theta as the principal argument, theta then, as you cross this point, cross this line here, theta then suddenly jumps to minus pi, and then it decreases and becomes less and less until theta goes back to 0. So really what we're saying is that if you look at log z, as you trace out a path of what z is doing, log z will have a sudden jump from I pi at this point, just above this point here, to minus I pi. So basically there's a line along which log z will suddenly jump. Now if you decide to make theta the principal argument, that line is the line theta equals pi. And we call that line a branch cut. And a branch cut of a function is a line along which there's a discontinuity, in the sense that the value of the function either side of that line jumps suddenly. So what does this branch, why are we talking about branches? Well, remember that in fact log z can be written like this, and normally we write it like this, where theta p is the principal argument. It's multi-valued. We can choose n to be any integer, and for each choice of n we call that a branch of log z. So with the principal branch, which we've also called capital LNZ, is simply when n is 0, and then we've got the branch corresponding to n equals 1, branch corresponding to n equals 2, and so on, or even n equals minus 1, minus 2, and so on. All of those are called separate branches. If we just look at log z of one branch at a time, if we define, if we consider log z in this way, then theta, the principal value of theta has a sudden jump at theta equals pi, jumps from pi to minus pi. So that's the origin of the discontinuity. Now this is of particular interest. So why are we interested in this? Well, it's basically because when we do integration around the complex plane, which we'll do shortly, a golden rule is that we're not allowed to integrate through a discontinuity. We're only allowed to integrate along paths where the function is smooth. So we have to always know where our function has a discontinuity, and we have to avoid those branch cuts. At least we're not allowed to cross those branch cuts. It turns out branch cuts are remarkably useful. They're nothing to be particularly worried about. We just need to know where they are. The other thing is that we can actually decide where to put the branch cut. You see, with theta p, we define theta p, the principal argument, to lie between pi and minus pi. But we can actually choose to say, well, actually, I want my log function, I want the theta in my log function to not vary between pi and minus pi. I can choose to make the theta in the log function in my branch of the log function to vary between any values separated by 2 pi that I like. So I could equally say, well, actually, I want my theta to vary between 0 and 2 pi, and that's allowed. So I can then say, oh, the branch I'm interested in is log z equals log r plus I theta, where theta has, I say, varies between 0 and 2 pi, in which case there'd now be a branch cut along theta equals 0, because log z will then have a sudden jump between these 2 points here. So at this point here, if I choose a circle r equals 1 again, log of a point here on the circle would be I times a very small number. But if I just cross this dotted line here, then log of z at this point would be I times nearly 2 pi. So I've gone all the way around and I've almost reached 2 pi. So I times almost 0 and I times 2 pi, a big difference. Okay, so there's a big difference in log z when I cross this dotted line. It doesn't happen anywhere else, you see. Now I've changed what theta is allowed to lie between 0 and 2 pi. This line, this point here is no longer a problem, because here theta is pi minus a little bit. Here theta is pi plus a bit. So I can make these 2 points get closer and closer, and there's no sudden jump anymore. Equally, I could choose that theta lies between phi and phi plus 2 pi, where I just change my branch cut to be any angle I like, which is going to be phi now. So now I just say that, okay, the theta has to lie between phi and any angle up to phi plus 2 pi. This is not terribly useful. Normally people choose to make the branch cut for log z either along theta equals pi or along theta equals 0.